Hey folks, so today we're going to talk a little bit about limits and also about infinite sums, more specifically infinite geometric sums. So let's get started. Let's evaluate each of these limits real quick. So take a minute and do so, pause it, find all these limits, or at least what you think these limits are, and then we will talk. So, first one, limit as n goes to infinity of 1 over n. Well, think about what happens as the number n gets bigger and bigger and bigger. The denominator is going to get bigger and bigger and bigger, which means the fraction is going to get smaller and smaller and smaller. And so the limit as n goes to infinity of 1 over n is going to be 0. Imagine if n was 100,000 million billion bajillion. 1 over a ridiculously huge number is essentially 0, and so this limit is equal to 0. What about this second one right here? As n goes to infinity, 2 times the expression n plus 3 quantity squared divided by 3n. Well, imagine what would happen if you were to expand the numerator. You would end up with an n squared term. I don't even care about any of the other terms. You're going to end up with an n squared term, which is going to cancel out with that n term. You'd be left with a factor of n in the numerator, which means this fraction is going to grow without bound. And so that limit would be infinity. Because the power of the numerator is greater than that power of the denominator, this fraction is going to infinity. This next one here, 1 to the n, well, it doesn't matter what n is. If the base of that exponent is 1, this limit is just going to be 1, so that's not very exciting. 1 to the 100 millionth is still 1. Well, what about this guy right here? 5 to the n over 4? Well, 5 to an increasingly large exponent is going to get bigger and bigger and bigger, and so this limit is also infinity. And what about this one right here? This one's kind of goofy. Negative number raised to a power. So think about what would be happening with these terms. Let's even just ignore that denominator for now. Imagine just negative 3. Imagine if n was 1. Well, if n was 1, then negative 3 to the first would be negative 3. But then if n was 2, negative 3 to the second would be positive 9. So we'd be going from negative 3 to positive 9. If n was 3, then we'd get negative 27. If n was 4, we get positive 81. So we're increasing by 3 to the n power, but it's continuing to change sign. And so we're going to say that this limit does not exist, because it's going to continually alternate between positive and negative, and it's not going to go to anything in specific. And then finally, this last one right here, well, 8 over 8, that's just going to go away. And let's think about this 1/2 to the n. Well, if you're continuing to raise a fraction like that, that is less than 1 and greater than negative 1, if you're raising a fraction like that to a power, that is going to correspond to this exponential graph, which is going to go to 0. And so this limit is 0. So there are 6 limits right there. Go ahead and take a look, make sure you understand the different scenarios, and we're going to use these in today's lesson. So objectives for the day are to come up with some sort of formula to evaluate an infinite sum of a geometric series. So to do so, we're going to look at the limit as n goes to infinity of the partial sum s sub n. Once we've come up with that, we're going to evaluate some infinite sums, and then we're going to use these partial and infinite sums to solve a couple different situations. So let's work through this real quick. We briefly discussed this in that do now. We're going to hit it home a little harder now. Limit as n goes to infinity of 5 to the n. Well, that is going to be infinity. Again, think about what would happen if n was getting bigger and bigger and bigger. So kind of think of this as a sequence. If n was 1, well, we'd get 5. If n was 2, we'd get 25. 5 cubed, 125, etc. It's going to continue and continue to grow without bound. It wouldn't make a difference if that number 5 was a 2 or a 3 or a 4 or a 99 or a 1000, as long as that base of that exponent is greater than 1, it's going to go into infinity. And so, if you think about what that means for this limit, if we take the partial sum s sub n, which is this bit right here, that's our formula for the partial sum. If you notice, if we're looking as n goes to infinity, the only term with an n is this r sub n. So if r is greater than 1, then r sub n will go to infinity. R sub n is going to go to infinity, which means if you think about it in that numerator, we're going to have 1 minus infinity, essentially, over 1 minus some positive r that's greater than 1. Well, the numerator, that's going to go to negative infinity. The denominator, that's going to be a negative number because r is bigger than 1, so those negatives will cancel out, and this limit would be infinity if we weren't looking at that a sub 1, which is essentially saying that whatever that first term is going to determine whether this limit is positive infinity or negative infinity. If the first term is positive, then the limit will be positive infinity. If the first term is negative, then the limit will be negative infinity. But if r is bigger than 1, it's going to be one of the infinities, either positive or negative, totally dependent upon that first term. All right, well, what about this? We talked about this briefly. The limit as n goes to infinity of negative 2 to the power of n. Again, think of this as a sequence. Our first term would be negative 2. Our second term would be 4, and then we'd have negative 8, and then we'd have 16, and then negative 32. If you think about this as an actual function, it's going to be like oscillating like that between positive and negative forever. And so this limit does not exist, which means if we then go to this limit right here, it's the same thing. If we have a negative number less than negative 1, this limit is going to continue to bounce between these numbers, and so this limit will not exist, which means then that this sum will not exist. So the infinite sum here, we really can't say equals anything because we'll have to say that this sum diverges. Now let's be careful here because this sum right here also diverges, but this sum diverges to either positive infinity or negative infinity, whereas this sum right here just diverges and not to anything in specific. It's going to bounce back and forth forever. So it just diverges. We can't get any useful information from it. All right, well, what about this? What about a fraction? 1/2. Well, again, let's think about this sequence. The first term would be 1/2, and then we'd have 1/4, and then we'd have 1/8, and then 1/16, etc., etc., etc. If you think about it as an exponential graph, it's going to look like that. It's going to tend towards 0. So that limit will be 0. And what about this guy? Well, this is going to be very similar. Our first term here would be negative 1/2. Our second term would be positive 1/4. And then we'd have negative 1/8. And then we'd have positive 1/16. So in this instance, we are going to get that like little weird, awkward, oscillating thing, but it is actually going to tend towards 0 this time because that denominator is going to continue to get bigger and bigger and bigger, which means the fraction is going to continue to get smaller and smaller and smaller. So even though it's negative, we are still going to tend towards that same 0, which is kind of cool and interesting and different. And so if r in general is between -1 and +1, this limit is actually going to be equal to 0, which is actually hugely important for us. So think about then what happens here. If we look at this infinite limit as the partial sum as the n value goes to infinity, this r sub n, we said, is going to go to 0. And so in the numerator, we're just going to have that 1. And so we have a sub 1 times 1 over 1 minus r, which we could rewrite as a sub 1 over 1 minus r, which is actually our definition of the infinite limit of a geometric series when r is between -1 and +1. Hugely, hugely important here, so make sure you jot this down right now. So let's hit this summary again real quick. If r is greater than 1, then the infinite sum of a geometric series will be either positive or negative infinity, depending upon the sign of the first term. If r is less than 1, then the series just simply diverges to nothing in particular. It's going to bounce between positive and negative numbers that get bigger and bigger and bigger. But if -1 is less than r and r is less than 1, so if r is between -1 and 1, then the infinite sum actually converges to a value which can be found by taking the first term and dividing it by 1 minus r. And again, this is what we're interested in. This is going to allow us to do interesting things. And let's use that interesting thing right now. So let's find the sum of the series S of n and express the series in sigma notation, and then calculate the infinite sum. So kind of some review, and then also this new stuff. So let's write the explicit formula. A sub n equals our first term, 120, times our common ratio. Well, what is our ratio? It's going to be 30 divided by 120. Cross those zeros out. 3 over 12 is the same as 1 over 4. So our ratio is 1/4, and then we're going to raise that to the power of n minus 1. So this term right here, we can set equal to a sub n and solve for n to figure out what number term this actually is. And to do so, we're going to first divide by 120. So we're going to have 15 over 120 equals this 1/4 to the power of n minus 1, which we will rewrite in log form as the log with a base of 1/4, same as the base of the exponent, with an argument of 15 1/20th, and that is equal to n minus 1. So I'm going to add 1 to both sides to set it equal to n, and crunch that number to figure out the term value, the term number of 15 over 128. Oh, and I'm just realizing I wrote 120 there. Wait, I did totally crazy things. Look, that was supposed to be over 128. So that denominator should actually be 15 divided by 128 divided by 120. So I'm going to jump all the way back to this stage. 15 over 128 equals our first term times our common ratio to the power of n minus 1. And now I'm going to divide by 120, which will make the left side of my equal sign 15 divided by 15,360. That equals 1/4 to the power of n minus 1. And now I can rewrite this in log form as the log with the same base, which is 1/4, with an argument of 15 divided by 15,360 will equal my n minus 1. So again, now I'm going to add 1 to both sides, which will then make this equal to n. And now we can figure out what the value of n is. What number term is this? And you will find that this is the 6th term. So we want to find the 6th partial sum, f sub x, 6, which will be the first term, 120, times 1 minus our ratio, which is 1/4, raised to the power of n, which is 6, divided by 1 minus 1/4. And crunch that number. And when you crunch that number, you get this absurd fraction, 20,475 128ths, which is roughly 159.961. So that is the 6th sum of this series. And now let's calculate the infinite sum. So to calculate the infinite sum, all you need to do is take the first term and divide it by 1 minus the common ratio, which is pretty nice. So the infinite sum of this series is going to be that first term, which is 120, divided by 1 minus our common ratio, which was 1/4, and we will get, you can actually do these by hand pretty easily, 120 divided by 3/4, 1 minus 1/4 is 3/4, so 120 divided by 3/4 is the same as 120 times 4/3. And 120 divided by 3 is 40. So we have 40 times 4. So we have 160 as this infinite sum, which was pretty gosh darn close to that sum right there, 159.961, which makes sense because look how small that fraction already is at the sixth term. It's already almost 159, and that fraction is small, so we're not adding that much more, but we do get exactly 160, which is pretty nice because, pretty numbers are pretty awesome. So one little application of this idea that we can use, assuming this pattern of red shading continues forever, what fraction of the triangle is shaded red? Verify your result by finding an infinite sum. So the idea here is you need to look at the whole triangle. So picture this as the giant big triangle, which we have split in essentially to these four pieces. And in the first sequence, look at just this first red shading right there and there. That is our first term. And what fraction of the triangle is that? Well, that is 1/2 of the triangle. So we're going to call our first term a sub 1, 1/2. So if you think about each of these pieces, this is a fourth of the triangle, and then we're taking that little bit that was a 1/4 of the triangle, and now we're splitting that up into the next red section, which is that bit right there, which is 1/2 of that 1/4. And another way to think about that is this bit that I've put the black around right there, that's the same as one of these red pieces, which has been split up like that right there. And what's shaded? Well, it's those pieces right there, which is half of that bit, which was 1/4 of the whole thing. So think about this sequence. Our first term was 1/2. Our second term was 1/16. Our third term would be these little red bitties right there, which is again going to be shrinking by that same amount. So what is that amount? Well, all you need to do to always find your ratio is take a term like 1/16 and divide it by the previous term like 1/2. And if you're taking a fraction like 1/16 or anything and dividing it by a fraction, dividing it by 1/2, that's the same as multiplying it by. I'm actually going to stop what I was saying right there because I totally just set this up incorrectly. I make mistakes. Whoa. Let's think about this again because it is now after 10 o'clock and I'm starting to get sleepy. So let's go piece by piece. Again, here's our big triangle right here. Boop, right there. Split up into 4 pieces. And what we're doing is we're thinking of the first piece as the first term in the sequence as the big red shaded pieces, which if you think of that as the fraction of the whole is 1/2. So our first term is 1/2. But then our next term is going to be the smaller red shaded pieces. So I'm going to shade them green just so we can distinguish between them. But there we have that next bit. And the red shaded pieces there are these right there. Now what fraction is that green of the whole? That green being that bit right there. Because whatever that fraction is, that is our second term in this sequence. Because we want to add all of these pieces to figure out what is that total fraction. Well, maybe it would help you to visualize this if we split all of these pieces up like that. Well, now, how many total pieces are there? Well, there is 4 in each of those 4 pieces, so there are 16 of them. But we have 1, 2 of them that are shaded. So we have 2/16 shaded, which is 1/8 of that total shape. And if you did the same thing with the next smaller red pieces, we'd be looking at these bits right here. And again, that is 1/4 smaller than the last one. And if you count each of these little pieces that I've now split it up into, you will see that there are 64 of these pieces. And we are now on the section where we're counting just those bottom 2 little red pieces to the very right there. That one and that one right there. So we have 2. out of 64, which is the same as 1 out of 32. And this pattern is going to continue forever as you continue to shade smaller and smaller pieces. So if you take 1/8 and divide it by 1/2, that's the same as 1/8 times 2, which is the same as 2/8, which is the same as 1/4. You see that your common ratio is in fact 1/4. And so we have a starting term of 1/2. We have a common ratio of 1/4. Raise that to the n minus first power. That would be our sequence right there. And we want to find the infinite series of that sequence, which means we take the first term, 1/2, divided by 1 minus the common ratio, which is 1/4. And now let's simplify. So we have 1/2 over 1 minus 1/4 is 3/4 right there. And we're going to simplify this further. 1/2 times 4/3 is the same if we turn it into a multiplication problem. And then what do we have? Well, we have 4/6, which is the same as 2/3. And 2/3 is the fraction that is shaded. And this verifies it mathematically, but we could look at it and we could actually figure out that it's 2/3 pretty easily just by being careful about how we look at pieces. So look at only that stuff right there. We see we have 1, 2, 3 pieces, and 2 of those pieces are shaded. And then look right there. We have 1, 2, 3 pieces, and 2 of them are shaded. And then look there, 1, 2, 3 of them are shaded. Boop, 1, 2, 3 of them are shaded. So in each of those little tiny pieces that you break it up into, 2 out of the 3 equally sized pieces are shaded. If that continues on forever, it should make logical sense that we end up with 2/3 as the ratio that is shaded. And there you have it. Infinite sums doing some cool things. I'm going to sleep.